measurement of T for a double probe, symmetrical case. This is the kind of curve that we are getting. So if you see, this will be say minus 100 volt, this will be say 100 volt. So an important point of concern here is the voltage range it needs to switch from the ion saturation to electron saturation. It needs 200 volt. That's the range it needs to make the transition. Now, if I have to express this mathematically, it is I is equal to I sat tan h function of E V divided by 2 TE. So this is the expression that relates I and V, which I have drawn here. So this has TE, so we can extract TE from this equation. If we do some mathematical operation, what people do is they differentiate this curve di by dv, which is I sat, tan h differentiation is sec h square EV by 2TE, and whatever is inside the function has to be differentiated with respect to V, which will give E divided by 2TE. So to simplify this and to get an absolute value for TE, I am going to put a special case di by dv at V is equal to 0. For this special case, the right hand side turn out to be I sat and secant of 0 is 1, so E divided by 2T. From this I can hook out T value, which is I sat E divided by 2 times di by dv at V is equal to 0. So this is the equation that people are using in order to estimate the electron temperature from a plasma for a double probe symmetrical arrangement. All the things over here can be figured out. Di by dv at V equal to 0 has to be estimated from the curve. E is a constant, I sat is a constant, everything else is a constant. Now, in order to know in which units we are going to get the electron temperature as per this equation, we can do small cross-checking by using the units for the right-hand side terms. ISERT has a unit ampere, E has a unit coulomb, and di by dv has a unit ampere by volt. So it is coulomb volt. Coulomb volt is nothing but energy in joules. So the electron temperature what we will be getting is going to be the energy, but in the units of joules. So we have to convert it to unit of EV. So electron temperature in EV is nothing but this whole term divided by E. So when I divide this term by E, that is the charge of electron, I am going to get it in EV. So it's nothing but I sat divided by 2 times di by dv at a special case V equal to 0. So this is the equation that people have been referring in papers and textbooks in order to estimate the electron temperature. So electron temperature is not going to be dependent on so many magical terms. It only depends on 2 terms. One is the slope, the other one is the saturation current. So how the slope varies gives a very good interpretation of what the electron temperature is. If the rate of change is very large, electron temperature is going to be very small. If rate of change is very small, it's going to be large. When we try to plug in the values what we got in the curve that in the experiments 2 days back, in the IV curve whatever we got, the saturation current is 6×10⁻⁹ ampere, and di by dV at V equal to 0 is 1.2 into 10⁻10 ampere per volt. So if we try to plug in the values, it is gonna be 6×10⁻⁹ divided by 1.2 into 10⁻⁻10, which will be 2 into 1.2 is 2.5 into -9 plus 10. So 10 minus 9 is 1, 10 to the power 1, which is 25 eV. This is the electron temperature estimated from the Cara that we got in the lab, and this is the maths behind it. Now this is too large. Now I tell you why this value is too large. As I told you, it depends on the rate of change. The rate of change needs to be very large to get a smaller EV in the range of 2 EV or 3 EV. Usually the double probe Cara for a low pressure plasma appears this way. The variation happens in such a small range. If we observe, the rate of change is very large. So the transition from the ion saturation to electron saturation happens in a matter of 10 volt, whereas in our curve it only happens in a matter of 200 volt. The rate of change is very small, the rate of change is very large. This is the problem. This is the issue why we are getting such a large value, and there is nothing wrong with the mathematics behind it. So what we can do is, we can put our probe straight into the atmospheric pressure plasma and check how the transition of the curve is. If the transition is very fast, if the slope is very steep, instead of this kind of such a slowly varying curve, then we have to figure out the correction factor. We have to plug it into this equation. Then probably that correction factor would give us the correct electron temperature. Otherwise, I don't feel any issues with the mathematical part. The issues right from the beginning in the curve is only with such a slowly varying curve. So the slope has to be really steep. This is what I am trying to express. And another important thing is, the pressure in which plasma is generated is 1 bar, and the vacuum pressure that we have right now is 500 millibar. So we don't have a pressure drop of even 1 order. There is not even 1 order drop. We don't even get 100 millibar pressure inside the vacuum. It is 500 millibar as of now. So there is no great deal of pressure drop that is happening here. That is a matter of concern which people can ask in reviews. What is the great deal of pressure difference you are actually talking about? If it is 1 millibar, 10 millibar, fine. At least if it is 100 millibar, that's okay. But there is no great deal of pressure variation. So that is another point of concern.